Hi everyone, this is Ms. Shea. In this video we will be looking at the emission spectrum. After watching this video, you will be able to describe the arrangement of electrons in the atom according to Bohr's model, determine the maximum number of electrons that can be held in an energy level, describe the relationship between color, wavelength, frequency, and energy across the electromagnetic spectrum, describe how emission spectra are produced, describe the relationship between the lines of the emission spectrum of hydrogen and the energy transitions to the first, second, and third energy levels, and distinguish between a continuous spectrum and a line spectrum. We'll look at Bohr's model first. Niels Bohr proposed that electrons circle the nucleus in fixed energy levels, also known as shells. As long as an electron remains in a shell, it never gains or loses energy. Electrons fill the shells with the lowest energy first, and the further an electron is away from the nucleus, the higher its energy. The maximum number of electrons that can be held in energy level 1, which is closest to the nucleus, is 2. The second energy level can hold a maximum of 8 electrons. The third energy level can hold a maximum of 18 electrons, and the fourth energy level can hold a maximum of 32 electrons. This pattern is described by 2n squared, where n is an integer representing the energy level. The electromagnetic spectrum shows the range of all types of electromagnetic radiation. From longest wavelength to shortest wavelength, the electromagnetic spectrum includes radio, microwave, infrared, visible light, ultraviolet, X-ray, and gamma ray. Visible light is further split into the 7 colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. This is true in terms of energy also. The longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. An emission spectrum is a range of wavelengths emitted by an atom when it is stimulated by heat or electricity. Here's how it works. Heating or electrifying an element can cause an electron to absorb energy and jump to a higher energy level. This is called the excited state. The excited state is unstable, so the electron releases a fixed amount of energy as light particles, known as photons, and returns to the original energy level or ground state. When the light that is emitted is passed through a prism onto a screen, an emission spectrum is produced. The emission spectrum looks like a series of colored lines on black background. Each line in the emission spectrum corresponds to the release of a different amount of energy, as different electrons return to ground state from the excited state. This picture shows you the process of how an emission spectrum is produced, specifically for hydrogen. The gas discharge tube contains hydrogen. When electricity is passed through the hydrogen gas, a purple light is produced. This light is passed through a prism, and the emission spectrum of hydrogen, consisting of 4 lines, is seen. Notice that the wavelengths of the lines in hydrogen's emission spectrum correspond with the wavelengths those colors would have in the visible spectrum. Every element produces a unique emission spectrum, so hydrogen's looks different from helium's and also different from iron's. Let's look at the emission spectrum of hydrogen in more detail. As the electron in the hydrogen atom transitions from a higher energy level to a lower energy level, electromagnetic radiation is released that corresponds to the energy difference between the energy levels. This means that if the electron falls a farther distance, higher energy photons are emitted. If the electron falls to energy level 1, then the photons emitted correspond to ultraviolet. If the electron falls to energy level 2, then the released photons correspond with visible light. And if the electron falls to energy level 3, then the released photons correspond with infrared. Looking even more closely at the transition to energy level 2, we see that the visible light that is released corresponds with different colors. An electron transitioning from energy level 3 to 2 is only falling a short distance, a low energy difference. So the released photon corresponds with the red line in hydrogen's emission spectrum, the lowest energy line. The next electron transition is from energy level 4 to 2, which is a higher energy difference. This transition corresponds to the cyan line in the emission spectrum of hydrogen. The blue line in the emission spectrum corresponds with the transition from energy level 5 to 2, an even higher energy color and difference. And the violet line corresponds with the transition from energy level 6 to 2. In the emission spectrum of hydrogen, we also see that the lines at shorter wavelength and higher energy are closer to each other. This gives us the evidence for the idea of convergence, which says that the farther out from the nucleus, the energy levels get closer together until they finally overlap and converge. Because wavelength, frequency, and energy of the lines in the emission spectrum are all mathematically related, if we know one value, then we can calculate the other two. There are two mathematical formulas that allow us to do this. C equals nu times lambda, and E equals h times nu. C is the speed of light, which is equal to 3.00 times 10 to the 8th meters per second. Nu is the frequency in inverse second, or hertz. Lambda is the wavelength in meters. E is the energy in joules, and h is Planck's constant, which is equal to 6.63 times 10 to the negative 34 joules seconds. Finally, we'll compare a continuous spectrum and a line spectrum. A continuous spectrum is produced when you pass white light through a prism. All of the frequencies or colors of visible light are shown. An emission spectrum is an example of a line spectrum, which has some of the frequencies or colors in the spectrum missing.